Look at a skyscraper. I mean, you look up, you see the steel beams, the poured concrete foundation.
Right, the physical stuff.
Exactly. You see the plumbing winding through the walls, and it's all entirely binary. The physical pipes are either connected or they aren't.
Yeah, water flows or it just doesn't.
Right. You can touch it, you can inspect it. But today, our mission is to explore the hidden architecture of the decentralized web. We are looking at a digital landscape that is completely invisible to the naked eye.
Completely invisible, but it moves billions of dollars a day.
It's staggering. It coordinates the economic actions of millions of people without a central authority. And for you listening, we have a massive stack of sources to get through today to really understand this invisible plumbing.
We really do.
Yeah, we're pulling from Ethereum and Solana developer documentation. We are digging deeply into Stellar's Soroban smart contract SDK, and we're going all the way to breaking news and highly advanced community GitHub repositories.
Some really wild stuff in those repos, honestly.
Oh, absolutely. And specifically concerning the Pi Network's massive transition to an open mainnet.
Because what we are really examining here is the structural integrity of a new internet. I mean, it's incredibly comforting to think of apps and websites as just, magic that happens behind the glass of our phone screens.
Yeah, you just tap a button and it works.
Right. But beneath that surface, the complexity required to make a decentralized network actually function is just staggering.
Totally. I want you to imagine building a digital economy from scratch.
Yeah.
And not just a boutique network for a few thousand crypto-native engineers.
No, an infrastructure meant for tens of millions of everyday people.
Exactly. How do you actually make the plumbing work at that scale?
Yeah.
How do mobile apps talk to a blockchain?
And how do scattered computers agree on the truth without boiling the oceans to power their processors?
Which is a huge issue, and maybe the most fascinating question of all. How does a closed mobile-first app transition into a quantum-resistant Web3 powerhouse while the whole world is literally watching?
It's a massive undertaking.
Okay, let's unpack this. Before we can talk about deploying advanced smart contracts or, tracking the daily unlock of millions of tokens, we have to understand the basic language these networks speak.
Right, because blockchains don't speak English.
No, they do not. They don't speak Python or Java natively either. They speak a very specific, unforgiving dialect. We need to look at the JSON RPC API.
Yeah, so JSON RPC stands for JavaScript Object Notation Remote Procedure Call, which is a mouthful.
It really is.
But to understand why this exists, you have to picture the architecture. If you were building a software application, let's say a digital wallet on your smartphone.
Or like a decentralized exchange in your browser.
Exactly. And you want it to interact with the Ethereum blockchain or Solana or Pi. It has to connect to a node. But your mobile app and the blockchain node are entirely separate entities. They're often living on totally different continents.
Right.
So the JSON RPC specification is the universal translator between the two. It's this uniform, stateless protocol.
And the sources emphasize that stateless nature heavily.
They do, because it ensures that no matter what specific client software a node is running under the hood, it can understand your app's formatted request, process it, and send a response back in a really lightweight JSON format.
Let's break down how Ethereum handles this, just to ground it.
Yeah.
Because they categorize their core methods into 3 distinct buckets, right? Gossip, state, and history.
Yeah, 3 distinct buckets.
So let's say I'm building an app that needs to know what is happening right now on the network. I'd be looking at the gossip methods, I assume.
Right. Gossip methods track the bleeding edge, like the absolute head of the chain. This is how nodes literally whisper to each other across the global network to propagate information.
Oh, I like that image. Whispering to each other.
Yeah. So if your app wants to know the most recent block number that was just mined, it calls block number. Or even more importantly, if your user hits send on a payment, your app uses xSendDraw transaction.
Okay, so you are taking your user's digitally signed data and throwing it into the network's gossip pool.
Exactly, the mempool. You throw it in there, hoping a validator picks it up and includes it in the next block.
But if I want to know the result of that transaction, or what a user's account looks like before they hit send, I have to move to the state methods, right?
You do. Our sources describe the state as one massive, globally shared piece of RAM.
Just one giant computer memory bank.
Basically, yeah.
Yeah.
This is the present moment crystallized. To check a user's funds, the app asks getBalance.
Makes sense.
Or to figure out how much computational effort a smart contract execution will require before you actually commit to it, You use the estimate gas.
And there's also eth get transaction count, right?
Yeah.
Which tells you how many transactions a specific address has ever sent.
Yes, that one is critical.
I imagine that's crucial for preventing replay attacks,
Right.
like where someone tries to broadcast your old transaction a second time just to drain your wallet.
It is the primary defense against replay attacks. Every transaction has a number used once.
A number used once, right?
So the network checks the current state via that transaction count. If the nonce on your incoming transaction doesn't match the expected next number in the state, the node rejects it outright.
It just shuts it down.
Exactly. And finally, you have the history methods. If the state is the RAM, history is the hard drive.
Ah, the permanent append-only ledger going all the way back to the Genesis block.
Exactly. So if an auditor needs to verify a complex decentralized finance trade from, say, 3 years ago, they call fgetBlock by hash.
And they feed in the exact cryptographic identifier of that historical block.
Right, and the node retrieves the immutable record.
Okay, but reading through the Ethereum documentation provided in our sources, it is definitely not as simple as typing, "Get me the balance of account A."
Oh, no, not at all.
The formatting rules are incredibly strict, like specifically around hexadecimal encoding.
They are brutal.
Yeah, when you are encoding quantities like a block number or a gas limit, you have to use hex, prefix it with 0x, and you absolutely must drop all leading zeros.
Which trips up a lot of new developers.
I bet. So the number 1024 becomes 0 by 400. And if your app sends 0 by 0400 with that extra 0, the node just throws an error.
Yep, it rejects it.
And the number 0.
Yeah.
It's literally just 0 by 0.
I know it feels pedantic, but there is a deeply logical machine-level reason for this. The node is trying to parse data as quickly and efficiently as possible.
Right, because scale matters.
Exactly. Leading zeros in a quantity don't add any mathematical value, they just add useless bytes to the payload. But the rules actually flip when you deal with unformatted data.
Wait, unformatted data like byte arrays or memory addresses?
Yes. For unformatted data, you still use the 0x prefix, but you must have an even number of digits.
Okay, so if you want to send a specific small piece of data, it has to be padded correctly, like 00004200.
Exactly. If you send 0x00000f, which has an odd number of digits, the JSON RPC just rejects it. The node expects precise byte alignments.
And the padding requirements get absolutely wild when you look at Ethget storage app. This blew my mind when I read it.
Oh yeah, retrieving specific map storage is wild.
Let's say a developer wants to retrieve a specific map storage element from a smart contract. For instance, finding out how many specific stablecoins I hold in a massive ERC20 contract.
Right, a very common query.
The app can't just ask the node, hey, how many coins does the host hold? The app has to calculate a KEKAK 256 hash.
And not just a simple hash either.
No. The app has to take my wallet address, pad it with exactly enough zeros to make it 32 bytes using a leftpad32 function, concatenate that with the memory position of the mapping variable inside the contract, pad that with zeros to 32 bytes, and then hash the whole massive string together.
It's a lot of manual string manipulation.
It's insane. Only then can they send that terrifying string of hex to the JSON RPC to get my balance back.
The reason for that intense 32-byte padding rule comes down to the fundamental architecture of the Ethereum virtual machine, the EVM.
Okay, so it's an EVM limitation.
Well, a design choice. The EVM operates on a 256-bit word size, and 256 bits is exactly 32 bytes.
Ah, I see.
The JSON RPC doesn't do the math or the formatting for you because, as we established, it is a lightweight, stateless protocol. The node expects you to do the heavy lifting on your end.
So you have to format the query so that it slots perfectly into the EVM's 32-byte memory slots.
Exactly. You are manually calculating memory pointers in a global decentralized state machine.
Now contrast that brutal manual memory mapping with Solana's approach, which is also detailed in our sources.
Yeah, Solana takes a very different path here.
They have a JSON RPC method called simulate transaction. This feels like a totally different philosophy.
It really is.
You can send a fully encoded transaction to the Solana node, and instead of committing it to the blockchain and making you pay for it, the node just pretends to run it.
Right, it runs a simulation against the current state.
And it returns incredibly valuable data, like the units consumed, which tells you exactly how much of your compute budget you just burned, and an array of logs so you can debug what went wrong in your smart contract.
But there's a catch, right?
Yeah, there's always a catch. It costs 160 credits to run this on their API service. And you have to encode your transaction in either base 58 or base 64, not hex.
So that simulation feature is an absolute necessity for modern development. Imagine trying to debug that Ethereum KEKAC 256 hash memory pointer issue we just talked about.
Oh man, that would be a nightmare.
But every single time you push a test transaction to see if it works, it costs you real money in gas fees.
Right, because you're actually writing to the chain.
Exactly. Solana's Simulate transaction lets developers dry run the execution state without the financial penalty. Well, assuming they pay the API provider's off-chain credit cost.
And the shift away from hex to base 58 or base 64 encoding.
That is simply Solana's native way of compressing data. Base 58 represents large numbers using alphanumeric characters, but it cleverly omits confusing lookalikes.
Like the number 0 and the capital letter O.
Exactly. It packs more data into fewer bytes than standard hex, which is absolutely vital for a high-throughput network like Solana.
Okay, so to visualize this entirely stateless architecture, the JSON RPC API is basically a waiter at a highly restrictive, pedantic restaurant.
I like this analogy.
The decentralized app is the customer sitting at the table. The blockchain node is the kitchen. You can't just walk into the kitchen and start cooking your own transaction.
No, health code violation.
Exactly. You have to give your order to the waiter, but this waiter refuses to speak plain English. You have to order using the standardized menu format.
Right, down to the exact byte.
If you want a steak, you can't say steak, you have to say 0 by 400. If you accidentally say 0 by 0400, the waiter just stares at you, rejects the order, and walks away.
And crucially, the waiter has total amnesia.
Right. They take your order, hand it to the kitchen, and immediately forget who you are.
The amnesia is the defining feature here. The node dedicates zero memory to tracking your app's session.
So whether your app is talking to the node over a standard HTTP web connection or a continuous WebSocket, every single request is an isolated event.
Every single one.
But if the node has complete amnesia, developers must be going crazy writing this from scratch. I mean, I assume they aren't actually sitting there manually calculating KEKAC 256 hashes and padding zeros perfectly every single time they want to build a simple check balance button.
No, nobody builds like that in production.
There have to be wrappers or libraries that automate this translation, right?
Absolutely. The sources specifically point to convenience libraries like web3.js, ethers.js, or the Solana Web3 library.
Okay, thank God for convenience libraries.
Yeah, to use your restaurant analogy, these libraries are like a highly skilled local guide sitting at the table with you. You tell the guide, I want to check my balance, in plain JavaScript.
And the guide rapidly translates that into the heavily padded 32-byte EVM-compliant hex string the waiter demands.
Exactly. The developer interacts with the clean, logical library, while the library handles the stateless, amnesiac, heavily encoded reality of the node in the background.
Okay, I get it now. So the JSON RPC API in these convenience libraries tell the node what we want to do. We've placed the order. But here is the multi-billion-dollar question.
This raises an important question.
Exactly. How do all the nodes in the network, all these different kitchens around the world, actually agree that the action happened?
Right.
Like if I spend 10 tokens, how do we prevent me from spending those same 10 tokens at a different restaurant across the street a millisecond later? We have the language, but now we need the mechanism of truth.
You're talking about consensus, which is literally the beating heart of any distributed ledger.
Because without it, you just have a mess.
Without a consensus mechanism, a blockchain is just a very slow, very expensive, and highly vulnerable database.
Very true.
Our sources from Stellar give us a great breakdown of the evolutionary steps here. First, you have proof of work, or PiBazar.eu.
That's Bitcoin's model, right?
Yes. It relies on mining, which is essentially a global competition to brute force complex cryptographic puzzles. It provides incredible battle-tested security, but the mechanism requires immense energy consumption and highly specialized, expensive hardware just to participate.
The brute force nature of PiBazar.eu requires huge energy grids just to keep the server farms cool. It's wild. Then the industry largely shifted toward proof of stake, POS, which is what Ethereum uses now.
Right, a major shift.
Instead of burning electricity to secure the network, validators stake or lock up their native cryptocurrency as collateral.
Exactly. If they validate honest transactions, they get randomized payouts.
But if they try to cheat or approve a fraudulent spend, the network slashes their staked capital. You basically replace the cost of electricity with the cost of capital.
But the Stellar sources introduce a third model, proof of agreement, or POA.
Oh, okay.
This is the foundation of the Stellar Consensus Protocol, or SCP. SCP does not rely on burning electricity to solve math problems.
And it doesn't rely on locking up massive amounts of capital to create financial hostages.
Exactly. Instead, nodes achieve consensus through a rapid-fire series of federated messages sent back and forth to confirm transactions.
Which is incredibly fast.
Very fast. Finalizing transactions in about 5 seconds, and it requires just a fraction of the computational overhead.
The mechanics of how SCP achieves this agreement without burning energy or staking money are fascinating. The documentation introduces two key architectural terms: quorum set and quorum slice.
These critical to understand.
From what the sources outline, a quorum set is the specific group of other nodes on the network that you, as a node operator, explicitly choose to trust.
Right.
And a quorum slice is the specific subset of that group that must agree on a transaction before you will accept it as valid.
Plus, there is a strict transparency requirement in this system.
Oh, the TOML file.
Yes. If you want your node to participate meaningfully, you must host a publicly verifiable TOML file on your domain that identifies who you are and what organization you represent.
So no anonymous miners hiding behind server racks.
Right. The speed and environmental benefits here are profound. Because you aren't waiting for a miner to solve an arbitrary cryptographic puzzle, the energy cost per transaction is practically negligible.
Yeah, this brings us directly to the Pi network sources.
Mm.
Pi is actually built on a highly modified version of Stellar Core.
Yes, they fork and modify it.
Pi chose SCP precisely because it allows for a massive, lightweight, mobile-first mining approach. You fundamentally couldn't have 50 million everyday people mining a proof-of-work coin like Bitcoin on their smartphones.
No, the processors would overheat immediately.
Exactly. The batteries would melt, and the data costs would be astronomical. SCP allows Pi to scale to an unprecedented number of human users because the consensus is reached through lightweight message passing, not hardware brute forcing.
And the sources show Pi is pushing this infrastructure to its absolute limits right now.
They really are. They are currently executing a massive network upgrade to protocol v20.2 with a mandatory node upgrade to v21.2 scheduled for April 6, 2026.
Which is a hard deadline.
The documentation is crystal clear. Any node operator who misses that deadline gets abruptly disconnected from the network.
They do not mess around with version control.
No. And the final step in this roadmap is a transition to Stellar Core v23.0 by May 18, 2026. That specific v23 upgrade seems to be the holy grail for them because it unlocks smart contract scalability for their 15.8 million migrated pioneers.
That sequence of upgrades from Protocol 21 to 23 is an absolute structural necessity.
Why so strict on the necessity?
Well, when you have a network with 15.8 million individual human users who hold actual migrated tokens on a live mainnet, the potential transaction volume is staggering.
Yeah, just think about if even a fraction of them log in at once.
Exactly. If even a fraction of those users try to interact with a decentralized app simultaneously, an older protocol would just choke.
It would crash completely.
So the network must have the expanded bandwidth and the finalized, optimized consensus logic of v23 to ensure those pioneers can transact without crashing the entire system under the weight of its own user base.
The Stellar documentation provided a great analogy for how this federated consensus actually works, which really helps wrap my head around it.
Oh, the classroom one.
Yes. They compared SCP to a group math test in a large classroom. You, as a student, pick a study group you trust. That is your quorum set.
Right.
You decide that you need a majority of your specific study group to agree on an answer before you confidently write it down on your test. That's your quorum slice.
Which ensures you aren't just relying on one smart kid who might be wrong.
Exactly. But to make sure the entire classroom arrives at the same correct answers, you don't just rely on your isolated small group. You rely on the fact that your group naturally overlaps with other groups.
Ah, the overlap is key.
Student A is in your group, but they are also in Student B's group across the room. Because these trusted groups overlap and intersect, the correct, verified answer propagates across the entire classroom in seconds.
If we connect this to the bigger picture, it's a highly elegant system, relying entirely on intersecting webs of trust rather than raw power.
But, I have to push back on the inherent vulnerability of that design.
Okay, let's hear it.
If you only connect to nodes you already know, and you only trust identified organizations in your designated quorum set, doesn't proof of agreement just recreate the centralized banking old boys club?
That is a very common critique, yes.
Right. You have a bunch of known, identified entities with their public TOML files just agreeing with each other behind closed doors. How is that a truly permissionless, decentralized network like Bitcoin, where anyone can join anonymously and mine?
It's a fair question, but the mathematical defense against the old boys club dynamic relies exactly on the overlapping nature of those quorum slices you just described.
How so?
Well, in a traditional banking cartel, trust is dictated top-down by a central clearinghouse. In SCP, trust is built bottom-up through reputation.
So no one is in charge of who trusts who.
Exactly. No single entity, not even the network creators, can dictate the global quorum because the slices naturally overlap. Node A trusts Node B, who trusts Node C, who trusts a university node, who trusts an independent developer node. It theoretically prevents isolated cliques from controlling the network state.
So it's basically a web of reputation.
Right. It replaces the reliance on raw hardware power in PoW or immense wealth in POS with a decentralized web of reputational trust.
But what if a node goes rogue?
If a large trusted node starts acting maliciously or approving bad transactions, the network doesn't need to overpower their hardware. The surrounding nodes simply remove the bad actor from their quorum sets, instantly isolating them from the network's consensus.
Oh, wow. They just effectively shun them.
Exactly, mathematical shunning.
Okay, so we have the language with JSON RPC wrappers, and we have nodes agreeing rapidly and cheaply using overlapping trust webs with SCP. But what are they actually agreeing on?
That is the next layer.
Right, they are agreeing on the execution of code. A blockchain needs to do more than just send basic currency back and forth to be a Web3 powerhouse. You need to build decentralized applications on top of it.
Which brings us to the smart contracts themselves, specifically Stellar's Soroban platform.
Soroban is Stellar's native smart contract platform, built specifically for this ecosystem.
And by extension, it represents the future of what Pi Network is building toward with their V23 Mainnet upgrade.
Right. Now, unlike older platforms that use proprietary languages, Soroban uses Rust as its primary programming language.
Which is hugely popular with developers.
The sources provide a highly detailed look at the Soroban Rust SDK deployment process, and it is overwhelmingly focused on one thing: extreme optimization.
They really obsess over file size.
The documentation goes incredibly deep into the cargo.toml production build optimizations.
Right.
When a developer has finished writing their smart contract and is getting ready to push their code to the live blockchain, they have to configure their release profile meticulously. They set opt level Z, which tells the Rust compiler to optimize the code for the smallest possible file size, completely ignoring execution speed.
They also set strip symbols.
What does that do?
It strips out all the helpful developer debug information, again, to save space.
And they set codegen units EAS1.
Now, that codegen units 1 parameter is particularly telling.
How so?
In standard software development, compilers will split your code into multiple units to compile them in parallel. It makes the build process much faster for the developer.
Right, multi-threading.
Exactly. But by forcing it to a single unit, the compiler takes much longer, but it can see the entire code base at once, allowing it to optimize and compress the final output far more efficiently.
Wow, so they are really sacrificing developer convenience for file size.
All of this aggressive tuning is because the Rust code is being compiled into WebAssembly, specifically targeting the WASM32 unknown environment.
And even after all that, once it's compiled to WASM, developers still run an optional Soroban CLI command to shrink the file even further.
Yeah, they squeeze every last bite out of it.
But with modern cloud computing like AWS, we are used to gigabytes of storage being practically free. Why is there this intense, almost obsessive focus on shaving a few kilobytes off a compiled WebAssembly file?
Because on a blockchain, block space is the most expensive digital real estate on Earth.
Because everyone has to store it.
Yes, every single byte costs money. You are asking thousands of independent nodes around the world to store your compiled code permanently in their RAM or fast solid-state storage.
Okay, yeah, that adds up.
If your smart contract is bloated with inefficient code and debug symbols, the transaction fee required to deploy it to the network will be exorbitant. By ruthlessly optimizing the WASM file size, developers save significant upfront capital.
And Soroban takes this cost-saving philosophy a massive step further with a fascinating two-step deployment process.
Yes, the two-step architecture.
First, you install the raw contract code onto the network. This gives you a unique code hash. You pay the heavy fee to store the bytes once. Then, step 2, you deploy multiple instances of the contract using that hash.
This two-step architecture drastically lowers the barrier to entry for decentralized app development.
Give me an example of how that works in practice.
Think about a standard token contract. If 100 different developers want to launch their own utility token or meme coin, they all fundamentally use the exact same underlying logic.
Right. Functions to mint, transfer, and check balances.
Exactly. In older systems, every single developer would upload that same code 100 times and pay the heavy storage fee 100 times, bloating the blockchain with identical data.
That sounds incredibly inefficient.
It is. In Soroban, the core token code is installed once. Then each developer just points to that existing code hash and instantiates their specific token name, symbol, and supply. It is a highly efficient reuse of on-chain resources.
It's exactly like buying a video game engine versus creating individual save files.
That's a perfect way to put it.
You don't re-download the entire 50-gigabyte Unreal Engine every time you start a new game of Fortnite.
Yeah.
You just create a tiny kilobyte-sized save file, the instance that points back to the massive engine code you already installed on your hard drive.
Precisely. You optimize the heavy lifting. Now, managing the actual user data generated by these deployed contracts brings up another unique Soroban feature.
Oh, contract storage and the time to live, or TTL.
Yes, the TTL.
The sources mention that developers and users have to actively extend the TTL using commands like ledgers to extend and durability persistent.
Right, they have to pay attention to it.
Wait a minute. If you are building a system based on immutable trust, isn't the time to live feature incredibly dangerous?
It definitely sounds scary.
If a developer forgets to run a script to extend the TTL, does user data like my decentralized identity profile or my token balances in a decentralized exchange just expire and vanish from the blockchain?
It sounds alarming from a user perspective.
Yeah, do I have to set a calendar reminder to pay a maintenance fee every year just to keep my crypto from disappearing?
Well, from an architectural standpoint, it is a necessary defense against state bloat.
State bloat.
Yeah. Older blockchains are currently suffocating under the weight of dead, unused, data-abandoned tokens, failed projects that nodes are forced to store in their fast RAM forever.
So they just fill up with garbage.
Exactly. Soroban solves this state bloat by requiring active maintenance. If data isn't being actively used or paid for, it expires and is evicted from the live expensive RAM, keeping the network lightning fast and cheap for active users.
But to answer my critical concern, the data isn't destroyed, right?
No, the data isn't destroyed. The blockchain acts like an iceberg. The data is simply moved from the fast RAM down into the deep, cold archival history of the ledger.
Okay, phew.
The sources explicitly detail a restore command. If your decentralized identity data expires, you or the app developer simply submit a restore transaction.
And what does that do?
The network pulls that data from the cold archival history, verifies its cryptographic integrity, and places it back into the active state. It perfectly balances the systemic need to prevent blockchain bloat with the user's guarantee of data permanence.
That is a brilliant compromise. It keeps the pipes clean without deleting the water.
Exactly.
And of course, before any of this code goes live on Mainnet, security is paramount. The sources reference the Scout Soroban examples repository, which shows that contracts must be ruthlessly tested on a standalone network using isolated Docker containers.
Security is non-negotiable here.
Developers utilize cryptographic identities and wrapped native tokens in these sandboxed environments to simulate real-world attacks. And the sources show external auditing firms like CoinFabric are actively reviewing these smart contracts to catch logical vulnerabilities before they go live.
Which proves that the tooling in this ecosystem is maturing rapidly. The ecosystem is moving from experimental phases into professional, institutional-grade infrastructure.
So we've built this incredibly optimized, cheap, lightning-fast infrastructure. We have the RPCs, the SEP consensus, and the Soroban contracts. But pristine infrastructure is useless without citizens to inhabit it.
It's just an empty city.
Right. What happens when you suddenly drop the gates and invite 15.8 million people to use it all at once? We need to talk about the current state of the Pi network and the massive migration they're currently executing.
Pi network is currently navigating one of the most complex, high-stakes maneuvers in the entire crypto space. They are transitioning from an enclosed mainnet to an open network.
Here's where it gets really interesting. Let's define those terms clearly based on the source because it's a very unique approach.
Sure.
The enclosed mainnet is a live, fully functioning Layer 1 blockchain ledger. Real transactions are happening, real balances are secured by the consensus protocol we just discussed. But it is blocked by a massive network-wide firewall. External nodes cannot connect to it. Third-party wallets like MetaMask cannot read it. Cross-chain bridges cannot interact with it. It is entirely self-contained.
It's a walled garden.
Exactly.
Yeah.
The open network, on the other hand, is when that firewall is permanently dropped, allowing the entire global Web3 ecosystem to plug in freely.
And the breaking news from April 1st and 2nd of 2026 shows just how close they are to dropping that wall. The Pi team just launched a dedicated RPC server on their testnet.
Which is a huge deal.
It is a massive shift for developers. Previously, app builders in the Pi ecosystem were restricted to using limited proprietary SDKs provided by the core team.
So they were handcuffed.
Basically. Now, by exposing the raw RPC server, developers have direct, unmediated access to the blockchain's inner workings. This is the absolute prerequisite for deploying the complex, custom Soroban-style smart contracts we just discussed.
Along with the RPC server, they also just launched the Pi Launchpad on the testnet. This is a structured platform specifically designed for community token launches.
And it introduces a very specific economic mechanic.
Right, differentiating between staking native PI tokens to secure an allocation size in a new project versus committing PI to actually purchase those new tokens.
That mechanic creates a vital new utility sink for the network.
Meaning it gives people a reason not to sell.
Exactly. It gives users a compelling financial reason to hold and lock up their tokens rather than just dumping them on a centralized exchange the moment the firewall drops.
But before any user can participate in the Launchpad or interact with these smart contracts on the mainnet, they have to pass through the network's most significant bottleneck.
The KYC.
Know your customer. The sources indicate KYC is the absolute gatekeeper for migrating from the mobile app to the 15.8 million pioneer-strong mainnet. And the logistical nightmare of this cannot be overstated.
It's a monumental task.
You have users from almost every country on Earth. That means the system has to process and verify over 150 different types of government IDs, passports, and driver's licenses.
And think about the varying quality of smartphone cameras.
Under completely different lighting conditions. They are heavily utilizing AI tooling to scale this identity verification process, using machine learning to parse the documents and match facial recognition data.
If the AI flags an inconsistency, it gets routed to human validators.
Right. If you don't pass both the AI and human checks, your mobile mined Pi never becomes real on-chain crypto. It's just gone.
The strategy behind the enclosed mainnet period makes complete sense when you view it through the lens of that KYC bottleneck.
How so?
By keeping the firewall up, the core team prevents external third parties, bots, or bad actors from dumping IOUs or exploiting the network's liquidity while they meticulously test these massive migration flows and refine the AI KYC gates.
So it provides a controlled, quarantined environment to ensure the plumbing holds under stress before they turn on the fire hose of global open market liquidity.
Exactly.
It's like a country with closed borders. Imagine a developing nation deciding to build its entire internal economy, its factories, its roads, its banking system, completely isolated from the rest of the world.
A total autarky.
Right. They figure out how to produce goods, pay their citizens, and trade internally first. Only after the internal economy is humming and they know who their citizens are, do they finally open their borders to global free trade. That is the enclosed mainnet strategy.
It's an accurate analogy for their development philosophy, but we also have to look impartially at the intense market realities of opening those borders. Our market analysis sources highlight a very volatile situation currently brewing.
The token unlocks, yeah.
There is immense structural pressure from token unlocks. Specifically, over 4.6 million migrated tokens are unlocking daily as users pass KYC and their vesting periods end.
4.6 million tokens every single day. And looking at the price data in the sources, Pi IOUs on exchanges have been trading in a tight range.
On-chain data suggests Whale's large institutional buyers are accumulating tokens between 0.1555 and 180 cents.
While retail sentiment among everyday users remains deeply bearish.
The sources indicate a classic market divergence. The data suggests large entities are quietly moving tokens off centralized exchanges into private custody, treating the 15-cent range as a hard floor.
Interesting.
Meanwhile, retail holders are increasingly frustrated by the delays in the KYC process and the prolonged enclosed nature of the network, leading to bearish sentiment and a desire to sell.
I have to challenge the math here.
Yeah.
Let's look at this tokenomics situation realistically. If there are 4.6 million tokens unlocking every single day and the price is hovering around 17 cents, that equates to nearly $800,000 of new supply entering the market daily.
It's a huge number.
If the borders open tomorrow, how can any new RPC server or community launchpad realistically absorb that much daily relentless sell pressure? Doesn't the hype completely outpace the mathematical reality of inflation?
As an impartial observer looking at the data provided, You are highlighting the exact formidable structural headwind the network faces. The 4.6 million daily unlock is a mathematical reality, and the inflation rate is severe. The large entities or whales accumulating at 0.1555 are essentially placing a bet.
A bet on what?
A bet that the upcoming open network utilities like the Pi Launchpad or the global PiFest merchant adoption events where users buy local goods with the token will generate enough real-world organic demand to outpace that daily inflation.
But if they don't?
If the network cannot generate seamless, everyday utility to absorb that massive supply, the sell pressure will inevitably dictate the market. It is a high-stakes, real-time battle between institutional accumulation betting on future utility and retail exhaustion driven by inflation.
To absorb that kind of monumental supply, the network needs more than just a token launchpad. It needs robust applications that easily pay users for their time and data.
And it needs users that can seamlessly pay applications for services.
The friction of spending the token has to be zero. That's where the developer tools come back into focus. We need to look at how apps actually integrate this economy.
The Pi SDK documentation provided in our sources outlines exactly how this microeconomy is supposed to function on a technical level. Specifically, it breaks down the architecture of app-to-user or A2U payments.
The documentation draws a very sharp distinction here between types of payments.
It does.
User-to-app or U2A payments, like you, the user, buying a digital sword in a Web3 game, require a complex double-check server-side approval flow to ensure the user isn't being scammed by a malicious app.
Which is good for consumer protection.
Exactly. But A2U payments, like that same game, rewarding you with 5 tokens for winning a tournament start entirely from the app server side.
The SDK walks developers through a very strict 6-step A2U process to execute that tournament reward. Step 1. The game server sends an API request to the central Pi backend to create a unique payment identifier.
Okay, pretty standard.
Step 2. The developer must load the winning user's account via the Stellar SDK to check its current state on the blockchain. Step 3. The developer builds the actual blockchain transaction, explicitly adding that payment identifier as a memo attached to the funds.
Like writing a note on a check.
Exactly. Step 4. The developer signs the transaction cryptographically with their app's secure secret seed. Step 5. The signed transaction is submitted directly to the Pi blockchain via the RPC nodes we discussed earlier.
And the final step?
Step 6. The game server hits the complete API endpoint on the Pi backend to finalize the loop and update the user interface.
You know, step 2 really stood out to me. The documentation highlights a crucial rule. Developers must load the user's account via the SDK every single time before submitting a transaction.
Every single time.
Even if the game app already has the user's wallet address saved perfectly in its database, it has to query the live blockchain first to make sure the wallet hasn't been destroyed or that the user hasn't rotated to a new active wallet address.
Because if a developer skips that verification step to save time and blindly sends funds to an inactive or dead address, the transaction will fail.
The tokens might be lost, but more importantly, the developer still has to pay the base transaction fee to the network for attempting a failed operation.
It's a costly mistake.
It's exactly like mailing an expensive package to a friend. You might have their address saved in your contact book from last year, but you call them first to make absolutely sure they haven't moved.
Right, checking first.
If you just mail it blindly and they've moved, the package is lost, and you still have to pay the post office for the wasted stamps. Loading the account checks the address and saves the developer the cost of wasted transaction fees.
And currently, the documentation notes a significant limitation in this flow. App developers can only process one single A2U payment at a time due to how sequence numbers work on the blockchain.
Remember the nonce we discussed earlier?
Yes. If a game tries to send 10 payments to 10 different tournament winners simultaneously from the same app wallet, the sequence numbers clash in the mempool and the transactions fail.
So they have to form a line.
Exactly. Developers currently have to queue them one by one. They have to wait for batch payments, which will group multiple operations into a single transaction to arrive in a future network update.
Okay, I have a major pushback here regarding the entire architecture of this flow.
Let's hear it.
If we are supposedly building a decentralized Web3 application, why do developers have to send HTTP requests to api.minepi.com in steps 1 and 6?
Ah, the centralized endpoint.
Yes. Doesn't relying on a centralized REST API endpoint controlled by the core team completely defeat the purpose of a decentralized blockchain? If that centralized backend server goes down for maintenance, the decentralized app stops paying its users.
What's fascinating here is That is the ultimate tension in Web3 design. And the deliberate compromise the architects made here is really interesting.
Why compromise?
Pi uses a dual-layered architecture. You have standard HTTPS REST APIs communicating with Pi's centralized backend, and you have the blockchain SDKs communicating with the decentralized Stellar-based ledger.
Right, but why split it at all?
For user experience and privacy, think about it. If an app sends you a payment and you want a push notification on your phone instantly, and you want a readable memo explaining what the payment was for.
True, I like push notifications.
But you absolutely don't want that plain text memo detailing your gaming habits or app purchases permanently etched onto a public blockchain for the whole world to read forever.
Oh, yeah, I didn't think about that.
By using the centralized backend to handle the metadata, the push notifications, and the user interface routing, while strictly using the decentralized blockchain for the immutable transfer of the underlying value, they protect user privacy.
So it's a trade-off.
It is a pragmatic acknowledgement that pure ideological decentralization often sacrifices user experience and privacy. They traded absolute architectural purity for functional, everyday usability.
Wow. Okay, so we've looked at the current pragmatic reality of Pi and Stellar. We've seen the compromises made to accommodate millions of users, but out on the absolute fringes of developer GitHubs.
Away from the official core team repos.
Yeah, away from the safe stuff.
Yeah.
There are experimental projects pushing this technology into outright science fiction. Let's look at what is coming next.
We were diving into some wild, community-driven GitHub repositories here, specifically from an open-source developer named Kusasi.
These repos represent the bleeding edge of experimentation in the ecosystem. The first repo is labeled Pi Supernode V25 Quantum Dawn.
It sounds like a movie title.
It really does. It claims to be slated for a 2026 release, and it prominently features post-quantum cryptography. Specifically, it lists integrating Kyber-124 KEMM and dilithium-5 signatures.
And the performance claims.
It claims the network will hit over 15,000 transactions per second across 64 separate shards with 2-second finality. It also integrates Groth16 ZK snarks for privacy and uses something called a Blake 3 VRF for leader election. This sounds like an alien spaceship compared to the current tech we just discussed.
It is heavily advanced, and we need to unpack the underlying mechanisms here to separate the science from the fiction.
Okay, dissect it for us.
While the official core team is conservatively transitioning to Protocol v23, this v25 repo is a community fork and experimental playground. However, the cryptographic concepts it relies on are very real and represent the existential fears of the current blockchain industry. Let's look at Kyber-134.
What's the threat there?
Blockchains today use ECDSA elliptic curve digital signature algorithm to secure wallets. It's virtually unbreakable by modern computers. But a sufficiently powerful quantum computer, using something called Shor's algorithm, could theoretically crack ECDSA in hours, compromising the entire global crypto market.
So a quantum computer could just steal everyone's money?
In theory, yes. Kyber-124 is a lattice-based cryptographic suite entirely compliant with the NIST Round 3 standards for post-quantum security. Implementing these post-quantum signatures is a real-world arms race happening right now.
And what about the Groth16 ZK snarks? What does that actually do for the network?
ZK snark stands for Zero Knowledge, Succinct Non-Interactive Argument of Knowledge.
Okay, that is a terrible acronym.
It really is. But it allows you to mathematically prove to the network that a transaction is valid or that you have enough funds to send a payment without revealing your balance or the transaction details to the nodes.
How is that even possible?
Imagine holding a Where's Waldo book.
Okay, I have it.
You want to prove to me that you found Waldo, but you don't want to show me where he is on the page.
Right.
You take a massive black sheet of paper, cut a tiny Waldo-sized hole in it, and place it over the book so only Waldo shows through. You proved you know where he is without revealing the coordinates.
That is a brilliant analogy.
ZK snarks do that mathematically, providing absolute privacy on a public ledger.
There's also another repo from the same developer for Pi Supernode V2020.1 labeled as production ready for the open mainnet. It features PostgreSQL 16 database integration for the nodes, QEIC, P2P transport, which claims 12 times faster syncing between nodes, and native bridges to Ethereum and Solana.
That repo is much more grounded in immediate pragmatic deployment needs.
Like things they actually need today.
Right. QUIC transport protocols, developed originally by Google to speed up web traffic, and cross-chain bridges are essential infrastructure for any isolated network preparing to enter the open mainnet phase and interact with external liquidity.
But then things get wonderfully weird.
Yep.
There's a third repo, the Stellar PiCoin SDK Singularity Nexus level.
Ah, the singularity nexus.
This appears to be a satirical or hyper-futuristic concept repo. It envisions the token as a stablecoin, permanently fixed at exactly $314,159.
Very specific number.
It boasts features like self-aware AI orchestration, holographic storage for eternal audit trails, and literal interdimensional bridging.
That repository is clearly playful hyperbole, exploring the absolute sci-fi extremes of where blockchain culture intersects with AI and futuristic tech.
That's pretty funny.
But even within the satire, it highlights the community's deepest desires. Absolute price stability via the fixed peg, and perfect incorruptible data retention via holographic storage.
It's like comparing cars. The official Pi Protocol V23 that requires the mandatory upgrades we talked about earlier, that is a reliable, street-legal, mass-produced sedan.
Gets you from A to B safely.
Exactly. It's built conservatively to get 15.8 million people to work safely every day. But the Singularity Nexus SDK and Quantum Dawn V25 repos, those are the concept cars at a high-end auto show.
They have gull-wing doors, nuclear batteries, and no steering wheel.
Yes. Some features, like the ZK snarks or QIC transport, will eventually be reverse-engineered into the production sedan. But some of it is just for show, to push the boundaries of imagination.
That captures the dynamic perfectly. The concept cars push the engineers to think bigger.
But wait, what are the macro implications of this? If the open source community is already out there, building quantum-resistant, AI-orchestrated 64 shard forks of the network, doesn't that risk totally fragmenting the user base before the open mainnet even fully stabilizes?
A chain split.
Right. If half the nodes decide to run the experimental V25 software with different consensus rules, the network splits.
It's a highly valid concern, and fragmentation is the historical bane of decentralized networks. But in the open source world, this kind of radical innovation on the fringes is a feature, not a bug.
How's a network split a feature?
It is decentralized research and development. The core team provides the stable, conservative V23 base layer to protect the billions of dollars in value.
Okay, the safe layer.
Meanwhile, brilliant community developers take on all the risk, experimenting with volatile, cutting-edge tech like lattice cryptography on isolated forks.
So they're doing the R&D for free.
Exactly. When the mainnet is stable and when the quantum threat becomes imminent in the real world, the core team doesn't have to invent the solution from scratch. They can adopt the best, most heavily battle-tested ideas from those experimental repos and integrate them safely into the official protocol.
Decentralized R&D. That is a brilliant way to conceptualize the chaos of open-source development. Well, we have covered an immense amount of ground today on our journey through the invisible plumbing of the decentralized web.
We really went deep.
We started by deciphering the foundational language of JSON RPCs and understanding why the EVM's 32-byte architecture forces strict hex encoding rules. We moved into the energy-efficient, fast-paced world of the Stellar Consensus Protocol.
Learning how overlapping webs of trust replace the brute force of mining.
We saw how developers use codegen units to shrink Soroban smart contracts down to the absolute byte to save deploy costs.
Fighting state bloat with the TTL.
Yes, and we tracked Pi Network's massive, high-stakes transition from a walled and closed mainnet to an open economy, grappling with the heavy mathematical reality of 4.6 million daily token unlocks and the logistical nightmare of AI KYC verification.
A truly massive migration.
We walked through the exact, pragmatic steps apps use to pay users while protecting their privacy off-chain. And finally, we peered into a quantum-resistant, ZK snark-powered future built by community visionaries on the fringes of GitHub.
It is a remarkable, accelerating evolution of digital infrastructure. We are watching the foundation of the next iteration of the internet being poured in real time.
It's exciting to watch.
But as we move toward these future systems that rely on things like Graph16 ZK snarks and post-quantum lattice cryptography, a profound philosophical issue emerges.
What's that?
The underlying math of these new privacy and security protocols is becoming so densely complex that no average human can read it, let alone verify it by hand.
Oh, wow. I wouldn't even know where to start.
Right. If the fundamental ethos of blockchain has always been don't trust, verify, what happens to our digital society when the verification process requires a PhD in quantum mechanics or relies entirely on an artificial intelligence to interpret the code for us? Can we truly trust a financial system that we can no longer intellectually comprehend?
That is a heavy, almost paradoxical question to leave hanging over our digital plumbing. Thank you for joining us on this deep dive into the architecture of tomorrow. Take that question, mull it over, and keep exploring the source material on your own. Until next time.